So these are my solutions to the Forrest homework problems that were due on November 24th, which is right before Thanksgiving break. So what I'm trying to do is include a PDF and explain my logic behind each one. I really want to see, for people who made the attempt, pretty good. But there's a lot of people who didn't, and it is going to burn your britches when we have quiz or test on those, and that's going to be before winter break. So, keeping things in mind, there are three real formulas that we've talked about using. I've had a whiteboard on those in class. I put them on Physics Classroom. It's been part of, he had puzzles. This is one of them. Newton's second law, F equals ma, as the other one. And the coefficient of friction one, which is force of friction is equal to a coefficient of friction times a normal force, is the third one. So in this case, what I'm really looking at here is thinking about the free body diagrams and the forces. And since these are not changing motion, I know the force up has to equal the force down. So if I want to think about this, technically the weight down, which is a gravitational force, is about 50 newtons. And I'm using 10 newtons per kilogram for my gravitational field strength. That's pretty much what we found in lab and class for purposes of Physics Classroom. They use 9.8 newtons per kilogram. So if you use 9.8, your answer might be a little different. For example, this would be 49 newtons. All right, so when I have this, I have a free body diagram pulling up the tension, and the downward force is the gravitational force. Those are equal to each other. So once I figure out the gravitational force, then the tension has got to be 50 newtons. Here, I've got two ropes pulling up, which would equal the 50 newtons down, so the tension in each rope is only 25 newtons. So what I did here with number 2, I can think about cable 1 and cable 2. Cable 2 is only holding up this 4 kilogram weight. Cable 1 is holding up both the 7 and the 4, or 11 kilograms. And actually, those are masses. So for cable 1, I circled everything in green. The tension up has got to equal the gravitational force down. So that's my weight is equal to mg. Weight is the same thing as a gravitational force for our purposes. So that's 110 newtons. So the tension in cable 1 is 110 newtons. For cable 2, I've circled this in purple as my system. So the force downward in this system is 40 newtons, which is 4 kilograms times 10 newtons per kilogram. The tension up has also got to be 40 newtons. For number 3, this is a little more challenging. So what you really want to think about here is the free body diagram on both these. If these two are connected to each other over this, and this is called an Atwood's machine, the 5 kilogram object will accelerate downward, the 2 kilogram object will accelerate upward. If these had the same mass, no matter where they're hanging, they wouldn't accelerate at all. So I need to think about the forces on the 5 kilogram and the forces on the 2 kilogram. The forces on the 5 kilogram are the gravitational force downward and the tension upward. On the 2 kilogram, I've got tension upward and gravitational force downward. So tension would be an internal force. It's pulling equally on both of these, which means it's really not part of the net force of the system. So this is a version of probably the most important formula, which is Newton's second law, and I'm going to take a look at that to get my answer. So this converts to 50 newtons if we use weight equals mg. This converts to 20 newtons. Now, if I end up thinking about my whole system here, I'm going to change this. If this is my system, everything in red, then I've got a total mass of 7 kilograms. 50 newtons is causing it to want to accelerate down on the left and up on the right. 20 newtons is acting down on the right, but will be pulling up on the left. So my net force is going to be 30 newtons. over 7 kilograms, that would give me 4.7 meters per second. 4.7 or 4.3 meters per second squared. For problem 13, which is at the top of the ones from physics classroom, what we end up finding is the diagram has two ropes similar to something we've seen before with free body diagrams, and they're both acting at the same angle, 34.5 degrees from the horizontal. So the key thing here is that since they're the same angle, the tension in each rope would be the same. Force up is equal to force downward. So we've got the tension up and the vertical component of that tension, which would be this tension multiplied by the sine of 34.5 degrees. That would give me the vertical component. And we've done things with trigonometry and vectors before. For this rope, and I'd have the same thing for this rope, although my drawing would be the mirror image of this. So each of these is going to equal the mg downward. So mg is the weight, the gravitational force downward, that's 431 newtons. Here, when I add these together, I get 2t sine of 34.5 degrees. And when I do the trigonometry for that in degree mode on my calculator, I get 1.133t. I get a t of about 380 newtons. If you got double this, it's because you only thought about one of the ropes, not both of them. And the big idea is noted over here. So this is 1b, not 16, by the way. And this should be 1a. We'll move that a down right here. Okay. At any rate, this is given the mass of an elephant. You're asked to find the weight on Earth. Very straightforward. It's a one-step problem. That's 60,000 newtons. The moon's gravitational field strength, and we learned about this in the Force of the Earth lab, is 1/6 of that of the Earth. And so I just take part 1a, divide by 6, I get 10,000 newtons on the moon. For problem 6, let me read the problem off for that. Hopefully you've got those around. This is a Air Force captain who's being accelerated. I changed the masses a bit from the physics classroom because they had each of these as 82 kilograms, which was confusing. So I had his sled with a mass of 95 kilograms. He had a mass of 82 kilograms. So the net force is the total mass times acceleration. That's, again, a version of Newton's second law. That gives us 79,600 newtons. For problem 7, we were given a net force and a mass, so we're asked to figure out the acceleration. That's very straightforward. Also, that's a one-step problem. For problem 14, it's a little bit more difficult. So the first part is construct a free body diagram when someone is pulling a wagon with person in it and there's friction. So it did say that there's a 24 Newton resistance force, a 52 Newton forward force from the tension. So this tension or pull is bigger than friction. The normal force up from the ground, so you could say for ground here, would be equal to the gravitational force downward. So I'm going to use this. Weight equals mg. Said that the total mass was the combined weight is 304 newtons. So if I rearrange that algebraically, I get the mass of the whole system of 30.4 kilograms. And once again, if you use 9.8 newtons per kilogram, you'll get a slightly different number. So for part B, it's asking determine the net force, mass, and acceleration of the wagon. The net force is just subtracting friction from the tension. The mass I got over here. The acceleration is going back and using those two factors in Newton's second law. So there's really several things going on here to get this acceleration. For problem 17, there's somebody skydiving out of a plane, Darren. Apparently he's a daring person, I guess. It's asking about the acceleration when his 82.5 kilogram body experiences 118 newtons of air resistance. So I drew a free body diagram, mass, drag force. So I used this formula to get the gravitational force. So that's the force down. Drag is acting upward with 118 newtons. The net force is 825 minus 118, all that over the mass, so that gives me 8.6 meters per second squared. And normally gravity would accelerate you at around 10 meters per second squared. So as Darren moves faster and faster, his weight would stay the same, so the gravitational force, therefore, stays the same. But as you're moving faster through the air resistance would increase, so therefore the net force and acceleration would decrease. For problem 21, we've got a rocket that's going upwards with an acceleration of 45.9 meters per second. It gives the mass of the rocket as 0.104 kilograms, and it's asking you to find the net force and the upward force of the thrust experienced by the rocket. So this is really important for me to draw this free body diagram. So the net force is the thrust minus the gravitational force downward. Well, I'm given the acceleration, I'm given the mass, so the net force, therefore, is those two multiplied by together, and that's about 4.77 newtons. But that's going to equal the thrust minus the gravitational force. So how much gravitational force do I have? Well, I go to the weight, or gravitational force, is equal to mg. Again, I'm using 10 newtons per kilogram. I get that as 1.04 newtons. So when I plug that back into this equation, thrust minus 1.04 newtons gives me this net force of 4.77 newtons. The thrust is 5.81 newtons. In other words, the thrust has to be bigger than the net force because gravity is acting downward. So that's an important aspect of this. And the big idea there is in pink. Problem 26 is our only problem where we're figuring out the coefficient, using the coefficient of friction formula. So in this case, we've got me applying a horizontal force to accelerate Mr. Spring. I'd give the acceleration rate, and I'd give you the coefficient of friction as 0.35. So the first thing is to draw a free body diagram. So the push has got to be bigger than the force of friction, and the upward and downward forces are equal. So remember, any perpendicular force is called a normal force, so that's what I put right here. So the first thing I'm going to do is figure out the weight, which is the force of gravity downward, that's 840 newtons. Since these two are equal, I can use this formula for the coefficient of friction. And remember, that's the Greek symbol mu, which simply stands for coefficient of friction and tells us how sticky or slippery a surface is. So I take that and multiply it by the normal force, which, as I said, is equal to the gravitational force, so that's 840 newtons. So I get the friction force as 294 newtons. Well, the net force is equal to m times a. We're given the mass of Mr. Spring and his acceleration, so that's 100.8 newtons. And I think in B, so that was the answer to B. And I already answered the force of friction above. I used that to get the net force. So really B and C should have been switched in terms of their order. So to find the pushing force, I know that the net force is equal to the push minus the friction. So I'm using my free body diagram to come up with a mathematical model. F net is equal to the bigger force subtracting the smaller force. And so now I can figure out that the push has to be greater than the force of friction by this amount. So I rearrange that algebraically and get around 395 newtons. So hopefully these are helpful to you in terms of seeing the answers. I did a lot of the examples anyhow, but you've really got to try them on your own before you become comfortable with things.